Yes, thank you. And that also is true also for other hardware like IBM machines, supercomputers like the former Blue Gene supercomputers and the successors. They use a different type of CPU, and that includes the encoding of numbers on that CPU. And that is what we call little and big endian. I will show that just here what it means. So what is a big endian number and what is a little endian number? So usually on a CPU or in physical memory, you have cells. And these cells have specific sizes, like for example, 8-bit, right? And these 8-bit cells or 16-bit cells, they can carry a certain fraction of a large number, right? Because on a large number, like in this case here, if you have, let's say, if you had 8 digits, you can separate the digits in groups of 2, and then it would fit in a cell, right? And each cell has an address. That is what you see here in hexadecimal code. So that would be the starting address, for example, would be here 400,000 in hexadecimal code. And then the next one is counted 0, 1, 2, 3, right? So if you had a large number, like a 64-bit or 128-bit integer number or floating point number, whatever it might be, in the big endian case, that would mean the parts of that number are separated into the different cells in the way as you see here. So 1, 2 is in the first cell, 3, 4 is in the next cell, and so on. And on the other hand, there is also so-called little endian types of CPUs, of processors, and these store the numbers in a different format. So if we look at the same addresses of the cells, like here, you see that the number is split in reversed order parts. Yeah, so you don't have 8, 7, 6, 5 and so on, but you have 7, 8, 5, 6, 3, 4, 1, 2. And that represents in the physical memory of the computer the same number, right? So that together is the exact same thing, just with 2 types of processors. And what happens then if you have binary files and you would store, like on a Sun machine, you open an IDL session and you store something in a binary file, and then you want to open it with your Fortran code, like with pencil code, on a different computer that has maybe Intel processors, then these don't fit, right? So the data simply doesn't match. So what comes out is garbage, or more or less garbage. It's let's say it's good data, but in a mixed order. Yeah. So that is the typical mistake that people do. They transfer binary files from one computer to the other, and then all of a sudden they find out, oh, that doesn't work. So I want to just quickly mention that concept exists, and so you are aware of. So if you change between different types of processors, you can look up if you have an Intel CPU, if it is big or little endian. And if you are working on a different computer with a different CPU, you better also check that it has the same so-called endianness. And that is the simple explanation of the thing. So the big endian is just the pig here, and the little endian is well, it's the same pig, but just in another order, right? So you have the second half first, basically, and then comes the rest. Okay, good. So let's come to the next more interesting topic, which is precision and the so-called machine epsilon. So that is whenever you compute something with floating point numbers, you never have perfect precision. Yeah, that is with integer numbers is clear. You have integer numbers, you have 1, 2, 3, 4, and so on. That is an absolute number. There's no error on it. But if you have a floating point number, if you have 0.01, for example, yeah, with a decimal point, then this is represented in physical memory in a different way than integer numbers, and we will see how it is done later. But the most important point here is there is no absolute precision, but instead what could happen, for example, if you have some rounding error due to the order of the computation, for example, there comes one such curiosity here. So let's say you first add x and y, and then you add to the result, you add z. And on the other hand, you can first add y and z, and then you could add x to the result, right? So mathematically, this is the same, but numerically, it is actually not. And that is an important point, which you have to get along with it, I mean, there's no way out of this problem. So the order of the computation can make a difference to the result, depending on how the rounding error are applied. That is what we call the machine epsilon, is the smallest number that you can just no more add. Yeah. So if you have one number like 1.0 here, and you add a very small number, let's say, I don't know, 10 to the minus 50, it could be that the result is again 1.0 and not 1.0000, etc. 1, right? Because that simply cannot be represented with a fixed given number of memory space. Yeah? So if you have, let's say, 32 bits for a floating point number, you have to live with it. There's a certain amount of significant digits, and whatever is below that threshold is simply lost. That is the rounding error. And in this case, the machine epsilon is exactly that number that can no more be added to 1 or to any other number. Okay. So how to estimate the epsilon? Well, you can do an approach like an iterative approach. You can try with given numbers. Let's say you have here such a formula for the epsilon in step n, for example. You take b half times b to the power of minus p. And then the starting values are these. So you start with b equals 2 and p0 equals 0.5. And then step by step, you can try if that number can still be added to 1 and the result is not 1. So let's say the equation, this equation is not fulfilled. So you have not found the epsilon. Then make it simply smaller, right? And doing it smaller is very simply with iterating p. So the next p that you will try, so pn plus 1 is the old p times b. Yeah, oh, sorry, making p larger means in the exponent with the minus, this becomes a smaller number then. And then you continue that, you iterate more and more until this equation here becomes true. And then you have found, let's say, at least an estimate for the machine epsilon. Yeah, because it's between en and between en plus 1 where first time the equation is fulfilled. Yes. So the machine epsilon can be found in such a way. You can do different schemes also if you want to get a bit more precise result. So with smaller steps, so to say, you change the formula a bit, and that is possible easily. What comes out if you test different numbers? So let's say starting with our equation, we had 1 as the number, and then we check for 1.0, what is the epsilon that we can still add? And we find this is about 10 to the minus, let's say 3 times 10 to the minus 20. Yes. So that is, in particular, this case here is double precision. In single precision, this is worse. In single precision, we are about 10 to the minus 7. Maybe some, depends a bit on which number you test. It can also be a bit smaller. What you see is, if you would test, for example, instead of 1, you would test, for example, the number 2, then the machine epsilon is, of course, different. Yeah. So the machine epsilon, if you look this double logarithmic plot, you could say has a fixed given ratio, and that ratio gives you, so to say, the amount of significant digits in that number in the test, so in your floating point number. So if you check, for example, for 1, you could say you have about 19 significant digits in double precision. Single precision, as I said, is only 7 maximum, maybe even less. And depending on the number, so if the number is larger, then the digits behind the floating point, the decimal point, is of course less. Yes, because you have 1 more digit in front of the decimal point. So let's say the length of the number, the significant digits, is always the same. It's about maybe 18 for double precision. Okay, does everyone understand what is meant with the machine epsilon? If not, then please ask. So, okay. Now, what is granularity? Well, as I said, there are numbers that you simply cannot add anymore. And the first time I experienced that was in the pencil code in 2008, when I had a simulation that was running quite a long time with a small time step. So I had the time of the simulation, Tn here, plus the delta t, gave me the new t, which is then Tn plus 1, right? So we had iteration maybe 1 million, added a small delta t, and then you should have had 1,000,001. Okay, so what happened is I had time of about 4,000 seconds, and I was running in single precision, and I wanted to add the time step, which was in this case 0.4 milliseconds, so 4 times 10 to the minus 4. And then it came out that the time didn't simply advance, it was simply stuck, right? And if you look at the digits here, you see easily that is about, if you take the ratio, that is about 10 to the minus 7, 10 to the minus 8. So that is around the machine precision. And that means at that time, even if you were running single precision, you couldn't advance the simulation anymore. Even if single precision was enough, it wasn't enough to store the time because the time advancement was too small as compared to the actual time. So it was basically smaller than epsilon. Yeah. Okay, so if you take the ratio, you see this is about 10 to the minus 7, which means you do have 7 significant digits in single precision, and that's it. But on the other hand, if the time step were by hand made larger, I saw then that the time advances and the simulation was not stuck, of course. So that means this number here is actually larger than the machine epsilon and could be added. Okay, so then the question was, well, does it affect only time, or is there any consequence for physical quantities in the pencil code? So I show you now granularity effects. So let's say we look at the density in a corona simulation, like a 3D MHD simulation. And then you see here, that is the pencil code GUI as you see it in single precision. You see here the background is colored with black and white, where white just means more dense than the background and black means less dense than the background. And what we see is, well, there's some kind of lines here, right? So if you have the 3 cuts, so this is one vertical cut, this is the other vertical cut, and then you have a horizontal cut through the 3D volume. And what you see is, well, there's black lines, right? And if you check the horizontal cut, you see that is actually an ellipse or so in the horizontal plane. And you see it even here in the plots. So these are the actual cuts. So if you go along this line here, you see these little dips, which is these black things here. So it was clearly significant. So it was not just rounding error. So we saw that in the density, obviously, there is a kind of effect, whatever that might be. Now in double precision, all of a sudden, this effect is gone. Yeah, so you see here, the density is totally flat. There's no such dips. And also you see there's slightly some less noise, right? If you look, this curve here is a bit noisy. If you go to double precision, it is absolutely smooth. Yes. So obviously there's a tiny effect. Well, then we thought, okay, we can live with it because in density, well, that doesn't really disturb us. And it's not a large thing, right? So we checked next the vertical velocity. So this is the z component of the velocity vector. And what we have, again, the same 3 cuts, so 2 vertical cuts, 1 horizontal plane. We see these kind of patterns. You could say zebra patterns almost. So if you look at the cut here along this line, then you see, okay, this oscillates back and forth. So actually positive and negative in a stripe pattern. And that is, of course, we thought is very nice because we have shear motion in the corona, and we were happy to see that. Now I show you the same simulation with double precision. And you see this is all gone. So that was a purely numerical effect that propagated through the differential equations and then created artificial structures that could be seen as a physical thing, but are actually not. Okay, so yes, so we were a bit astounded, I must say. Let's have a look at the next quantity, which is maybe the current density in the corona, because the current density sets the heating rate in the corona. So if you want to study coronal heating, then you are sensitive to the current density because the heating is basically proportional to J squared. And J squared, by the way, is nothing else, is proportional to the rotation of the vector potential A. Okay, so here's our image in single precision. And it, of course, looks totally fascinating, right? Isn't it? So you have all these small scale structures here. And yeah, I can just disappoint you. If you go to double precision, it looks like that. So everything is completely smooth. And by the way, if you look, here at the cuts, so along the horizontal line in single precision, you see this cut here, and the curve is oscillating up and down. And that is actually a kind of a numerical error, which is actually similar in amplitude than the quantity itself. Yes. So thinking back, in the density, the error was tiny. In the vertical velocities, we had regions with strong errors, but other regions were okay. If we look at the current density, we actually see more errors than the actual quantity. Yes, because if you go to double precision, so consider this noisy curve here, if you go to double precision, that becomes totally smooth. Yes. And the important point is, because if you take the coronal heating, you take J squared, right? So you have a quantity with some error and you square it. That means the error does not cancel out. And that is an important point. And since then, we of course switched to double precision only because, well, otherwise our coronal heating would be artificial. Yes. Now, how does it come, right? So the question is, how can the error become so large? So there is a nice paper from David Goldberg. It is called "What Every Computer Scientist Should Know About Floating Point Arithmetic." That was in 1991. I would say today that is should be renamed to "What Every Scientist Should Know," right? Because practically everyone is working with computers, and that means with floating point numbers, and that means with has to deal with rounding errors, etc. So the effect is called catastrophic cancellation. So we look at, for example, the rotation of A is proportional to B, of course, and the rotation of B is proportional to J. So what would happen in the corona? Let's take just the Z component of the current density J here. So that is, of course, proportional to the derivative of By in the X direction minus the derivative of Bx in the Y direction, right? So that is simply the component of the Z component of J. So unfortunately, in the corona, there is no physical cause why Bx should be significantly different than By. So those quantities are approximately similar. But that means also the derivatives are of a similar order, let's say, at least. Yeah. So now what happens is, well, if you set this in and those quantities are similar, you are subtracting two quantities with some rounding error from each other. And then the result is just about 2 times epsilon, right? So that is simply 2 times your machine precision, because maybe these numbers do have some rounding errors, but if you have 2 large numbers with quite some rounding error and you make the subtraction, just the rounding error remains, right? And that is, of course, catastrophic then. So therefore, yeah. So therefore, we see this large amount of noise, even though the quantity J was not used in the computation directly. I mean, we do not compute J directly. We use it, of course, in the heating term, yes. So that means these large rounding errors may not be in the direct quantities, they may be in the derived quantities. So if you want to check for such effects, you have to look basically all quantities that you use. And then you see maybe that there is a strong error in it or not. Okay, I want to go quickly talking a bit about how a CPU is constructed. Maybe we can leave the slides so that everyone can look then after the lecture with more time. But for a very quick overview, I want to say, so a CPU is a calculating unit, basically. And you do have registers to put addresses of memory places or storage addresses and actual data. And then you have a so-called arithmetic logic unit, which executes the instructions that come from the program. And these instructions include, for example, logical instructions like AND, or bitwise inversion. It includes integer addition, bit operations like shifting every bit to the left or to the right, and checking conditions like if conditions, etc. You have some kind of bus. The bus is basically a connection line between memory and periphery and the CPU subunits. And then what is important is on the CPU or near the CPU, we do have some kind of cache. The cache is used at different levels and with different sizes to accelerate accessing the memory. So if you want to read something from memory into the CPU, that takes time, because the memory is on the main board is distinct from the CPU, and you actually need to send an address to the memory chip. The memory chip looks up the place and transfers the result to the CPU, right? That costs time. So therefore we have the caches, and the caches are usually called L1, L2, L3, depending on what your CPU has. Sometimes they only have L1 and L2 or so. L1 is the fastest cache, but usually also the smallest, and it is very close to the CPU, maybe usually on the CPU. And then the L3 cache is of course largest, but is the slowest cache, but still faster than reading the actual memory. So that concept needs to be understood. So you have caches which allow you to accelerate reading the same data over and over again. Let's say if you have some memory block on the memory and you want to read a number and then the next number, if the whole block gets transferred to the cache, you can then read it very quickly. Yeah, so that is important. We will discuss this also in the next lecture also. And yes, and then of course you have some kind of floating point unit. That is what we call an FPU. And this one does calculations on floating point numbers following the IEEE standard. So that is standardized, of course. This includes floating point multiplication, division, power, trigonometric functions like sine and cosine, etc. So all these are standardized and are performed in a similar or almost identical way on different computer chips. Okay. So yeah, the text format is a bit jumping around here. Sorry for that. But we have address and data registers. So that is important for software developers. On a CPU, we have the address register, which says or which holds the position of the physical memory where your data is located. And then you have the data registered, where the actual data is transferred to the CPU where it can then later be used to calculate something like plus, minus, whatever. And this is a simple schematic how such registers look like a Motorola chip has 8 data registers and 9 address registers. It has one register which basically points to the point in memory where your program is at the current moment. So it actually points to the line of your code that is currently executed. And then you have a status register, which basically says like there's an error or there's no error. And Intel CPUs are organized in a similar way. I don't want to go too much into detail here. That is a block diagram. So here are the registers. The memory is accessed through this bus control unit or logic, and then reads data and stores data. And then you have temporary registers next to the algorithmic processing unit, so like here. And then these creates, of course, results that you can store back to the memory. And of course, the instructions from the program are also read into such a queue. So you hold on the CPU maybe the next 4, 5, 6 instructions, and then these instructions are executed one after the other. So this is how a CPU looks like if you open it up and make a photograph. So that is 486 CPUs. That is around the mid 1990s, for example. And you see here the connections between the pins where the CPU is sorted on the main board, and this is the different, the design of the CPU. You can see here what is actually shown. So the control unit is here, this block 1. Then you have the data path where the data is loaded in and prepared for the processing. Then you have the instruction decoder, which is the part 3 here. That is some microcode that basically tells what instruction should call which command on the ALU. And then you have some memory interface to load and store the data. Here's the L1 cache shown, which basically holds a fraction of your memory, and hopefully all the data you need is in there. So because then you can access it very quickly. And then here in part 7, there is the FPU, which computes all the floating point operations. I have some nice videos for you if you want. You can have a look in the break. So what I find particularly interesting is this set here, how to build an 8-bit CPU. It shows you on a little board, really with visible parts, so electronic parts, how to set up a CPU and how it actually works and operates. Yes, the floating point arithmetic I want to show you quickly. So this is a single precision 32 bits floating point number. What you have, for example, here is represented this number. What you have is the first bit gives you the sign, which is plus or minus. So it means 0 or 1 represents plus or minus. Then you have the exponent of the number, and you have the actual fraction of the number. So what you do here is, for example, this number can be represented as -1 to the power of the sign times 2 to the power of the exponent times 1 point fraction in base 2, so in binary format. Yeah. So that would mean this number is then represented in this way, for example. Here's some more representations of special numbers. If you want to look it up, you can. So for example, -2 looks like this, right? There's a minus, there's the 2, and the exponent is just 1, and the rest is 0. And that gives you, if you follow that formula, gives you a -2. And the 0, of course, is all bits are 0. There are some special numbers like infinity. They have reserved bit patterns. And double precision is, of course, the same, but with more bits. Like, for example, the exponent is longer and the fraction is longer. The sign is, of course, always 1 bit, of course. Yes. And then the floating point unit, how would it work? So you have the addition, or what we call the adder. So you have represented here an example like x and y is, well, that is what we call the mantissa. And this is what we call the exponent. So you have x and y with different mantissas and different exponents. So you can represent it as, for example, a times 10 to the power of small a, and the other one as b times 10 to the power of small b. And then if you want to add these two numbers, what you do is you put in the exponents here on this float chain, and you put the mantissas on here. And you can actually, first step, you compare the exponent by subtraction. So you take, in this case, you take 3 minus 2, and that gives you a 1, right? So there is a difference. So that means first step is to align the mantissas. So you convert the second number to have the same exponent as the first number. And that means you convert from 0.082 to 0.082, and then times 10 to the power of 3. So that's the same number, but with a different exponent. In this step, actually, you lose a bit of precision. And now, next would be set the new exponent to 3. So we have done that now. And then you add the mantissas, right? So you have 0.9504 and the 0.082 from here. Add this together and you get 1 point something. So that is obviously larger than what we want. So we have to shift the exponent again in order to represent it with our standard format. So what we do is we normalize the result so that we have something 0 point, etc. So the new fraction would then be 10324. And then we adjust the exponent, which is then times 10 to the power 4, right? And that would be the final result. And then you can put out the new exponent 4 and the new mantissa as given here, and that gives you the sum of x and y in this case. So this is how the CPU performs the operation physically on the chip. And multiplication is quite similar. So for multiplication, what you have to do is first you add, of course, the exponents, and then you do a multiplication of the two mantissas, and then you normalize the result again to a new exponent that fits to the representation in the computer. Then you have a result exponent and a result mantissa. So that is quite easy task, I would say, once you have the multiplication done, of course. Yes, that is how a floating point unit used to look like in ancient time. So you see here an image actually at NASA from a floating point unit standing here. Yeah, that is the actual device at that time when we did not have yet integrated circuits. Later, of course, FPUs were done on chips, like shown here. And there you see the actual chip inside if you open the chip. And then you see, well, the connections here to the pins, of course, and that is the actual FPU here that you can see. Well, this is just a quick overview on the schematic of an FPU. And I must say, as you see, this is 1964. So this is the old machine that worked, let's say, electrically, and this is the electronic machine working with the chip. This schematic is practically equivalent, and that is still the case today. Yes. Okay. Since time is up, I would say I stop here with the SMD unit, and then we can continue in the evening. Okay. Are there any questions?
Yeah, let me see. Yeah, there's a hand by Satyam. So Satyam, you can unmute and.
Hello.
Yes.
Yeah, so the slide where you explained about the calculation of JZ, so you said that when JZ is equivalent to 2 epsilon, so that is a problem. I could not understand why that was actually a problem and how to resolve that.
Yes. So the problem is mainly that if you take the two derivatives of bx and by, then they do carry some rounding error, right? And the derivatives are of a similar magnitude. So that means if you take the difference of it, you have 2 times the rounding error, basically. And the problem is, of course, if you look at the single precision here, you see this is all that structure that you see is all rounding errors. It's not real. It's not physical, right? And if you compute the heating in the corona, you square that. And that means the error does not average out. It is squared, right? And compared to double precision, that is, of course, much less heating. In this case, if you square this quantity versus the single precision quantity, then the heating in single precision is, of course, much larger than in double precision. So, and that is the main problem. Is that, did it become clear?
So essentially, whatever quantities we are calculating must be done in double precision, right?
Well, yes. If you see such a problem with rounding errors in any of these quantities that you use, then you should use double precision. Yes.
Okay. Okay. Thank you. Thank you.
Good.
I think Simon has a question. So was it Simon or?
Yes, thanks. So I just want to second what Philippe said about rounding errors and derivatives, because that's something I experienced myself in a different code that I developed with. And the problem was exactly where you take derivatives. So where we had very similar quantities and take the difference of very similar quantities and you get a huge error in that. And then of course, double precision can fix it. If it doesn't fix it, you might go even to quad precision. But one way around that is by, I mean, it doesn't always work, but one way around it is to change the order of your operations when you take differences. Now, of course, that always depends on the exact operations. You know, if you're taking curl operations, and maybe also depend on the order of your finite difference stencil. But it gives you a little bit of hope to use still floating precision by conveniently rearranging the terms. But again, it might not always work. But Philippe, do you think that's something people have looked at in the pencil code?
Yeah, some people have. Okay. Some people have, yes. I have. Okay. I had to, yes. But yeah, no. I want, with saying this, I want to actually make people sensible to the topic. And so that people see that it has real consequences in simulations. It depends, of course, on your setup, what you're running, if 7 digits is enough or not. But for the corona, I can say it is not. Yes. Okay.
Do you think we should have like a mechanism in the pencil code that tells you that, you know, a warning that you might need double precision?
Yeah, it's very difficult to implement. Yes. No, people have to check also derived quantities. That's the point.
Yeah, exactly.
Yeah. Okay. I have another appointment, so I would say